Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be wrapping up the chapter by taking a close look at bonds. And we're going to be looking at what does it really mean to be a single bond versus a double bond versus a triple bond. And without getting into the quantum mechanics, we have essentially two really good observable ways to look at bonds. The first of which is physically, how far separated are my two nuclei? And what happens is I increase the number of electrons that they tend to share. So, for example, let's say I'm looking at a carbon-carbon bond. If these two atoms are tied together by only a single pair of electrons, they tend to be separated by about 154 picometers, or this is also known as 1.5 angstroms, or 0.15 nanometers. So these are fairly close. Now, if I put two more electrons in between these two carbon atoms, they're now tied together by 4 electrons, and the distance closes down a little bit. And if I put 2 more electrons, it closes down even a little bit more. And we kind of see this again with most of our molecules. As I slowly add more electrons to the system, these two nuclei are pulled together tighter and tighter, indicating a tighter interaction. However, this doesn't tell us a lot about the stability, but it does say that there's less, that these two atoms are more willing to put up with each other. Well, let's take a quick look at these bonds using another metric. This is called bond dissociation energy. The major idea here is how much energy is required to break a bond. Because remember, these two atoms are only going to stay together if it's favorable to do so. If I put in a little bit of energy, think about something like combustion, I can make these two atoms start to fly apart. Enough energy, you can break any bond. So oftentimes we provide this energy in the form of heat, in which case these are often labeled as bond enthalpies. So for example, it takes about 440 kilojoules to break apart a mole of hydrogen-hydrogen bonds. However, if I'm looking at carbon-carbon bonds, it can be a little bit less, as I can take something like ethane and break it apart into 2 methyl groups. And we can use these metrics to evaluate the stability of various molecular bonds. So let's take a quick look and see what happens as I increase the number of electrons joining these atoms. So let's again take a look at carbon-carbon. So carbon-carbon bond is relatively stable, 347. There are plenty of bonds that are more stable, but it's pretty good. It's twice as good as nitrogen, and about 2.5 times as good as oxygen. So overall, it's a pretty good bond. But what happens when instead of having 2 electrons joining these 2 carbon atoms together, I put in an extra 2 electrons and I go to make a double bond? At this point, the bond is a little bit less than twice as stable. And this actually brings in a good point, that it isn't simply I double the amount of electrons holding the system together, I double the stability. I improve it drastically, but it's not always an even scaling. So it is worth noting that a double bond doesn't mean I just have 2 single bonds worth of energy. However, it is far more stable than a single bond. However, it is possible to break a double bond to make a single bond, and this becomes a big area of a big topic in organic chemistry. But for our sake, one of the things I want you to focus on is as we increase the number of electrons, binding together our atoms, we slowly make it harder and harder to separate. Now, what we're going to be doing in the next chapter is looking at a little bit more detail of why this is the case and trying to actually figure out exactly how electrons tie together these atomic centers. However, to do so, we're going to have to make a quick return to orbital theory. Until then, take care.